Hello, this is Greg Ristopin from Olympus. Welcome to this webinar on inspecting HVAC and heat exchangers using the NORTEC 600D Flaw Detector. Tube testing can be confusing, but this webinar should help demystify it by exploring the theory behind tube testing and showing a complete hands-on demo using the NORTEC 600D Flaw Detector with the HVAC and Heat Exchanger kit. Our presenter today is Terrence Burke. Terrence is a product applications leader for eddy current and bond testing products based in Quebec City, Canada. His responsibilities include conducting training on Olympus eddy current products and supporting customers about tube testing. This informational webinar has been scheduled for about an hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we're not able to get to your questions during the webinar, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Terrence Burke. Terrence, take it away.
Thank you, Greg. So today we'll be looking at the HVAC and Heat Exchanger tubing kit and the NORTEC 600D Flaw Detector. Tube testing made easy. So today's agenda looks like the following, as so. So we're going to look at why we inspect exchangers, the types of defects, the challenges, solution, what's in the box. We'll also review the eddy current technology, remote field technology, and near field technology, just to give you a good idea of what's going on. Before going to a live demonstration, I have a few key points I just want to highlight. Then we'll have a eddy current testing demonstration, remote field, and near field. All demos will be done with a differential as well as an absolute signal. You'll get to see the difference. We'll have a don't forget, just a little reminder before we call it quits, and finally the conclusion. So, why do we need to inspect exchangers? Well, first and foremost is to keep people safe. So, exchangers tend to have a lot of different types of fluids flowing inside them. Some are safe, some are acids, some are bases. So, we really don't want those things to leak into the environment. The environment can be the plant, the environment can be anywhere else. So we want to keep people safe. Now, for the plant owner, why would they want to inspect their exchanger? Well, it's to know the life of the equipment. If their equipment is still in very good shape, they'll be very happy. They'll use it for many more years. If the equipment starts to deteriorate, they want to know quickly before it's too late. So the sooner they know, the better they can figure out how to replace it, when to replace it, and so forth. There's nothing worse than having a heat exchanger that's actually leaking because you have fluid mixing together, and if it actually leaks out of the exchanger, it goes into the environment. And I know I've said it before, but environmental reasons, because once again, we're using acids, bases, chemical compounds inside these exchangers. So we don't want whatever is flowing to go into the environment and cause damage to the earth, people, and so forth. So that's why we inspect exchangers. Now, what types of defects can we expect? All right, we're going to start over here with wear to support plate. So in this case, what happens is you have a soft material, which is the tube, which is rubbing on a harder material, which is usually carbon steel, and that's a support. So you have rubbing from the tube onto the carbon steel, and what's going to happen is the softer metal will wear out. So here we have clearly a pit or a hole in the tube, which was under the support, and basically with a bit of vibrations or so forth and so forth, maybe a bit of liquid would just accumulate here and rest. Well, we have this pit that was created. Now, pits can also happen on the inside. Here we have internal pitting. Same thing. If you're using a very corrosive material inside the tube, pitting could occur. And once you start getting some pits, you get more pits, and before you know it, you have a lot of pits. So you have wall loss, you have pits, and the problem with pits is they can actually sometimes lead to holes. Now in this case, it's failure due to steam. So it's basically the steam is attacking the tube and creating pits here, or even a hole. So you have to be very careful when dealing with anything like that. Now, another one that could happen is what we call a taper defect, and that's tube to tube wear. So if your tubes are actually too close and there's vibration, the tubes could actually start rubbing on each other and creating, as you can see here, flat surfaces. So these flat surfaces are basically wall loss. So you don't want that. So you want to be able to measure that and to make sure that your tubes still have all the wall thickness necessary to avoid any problems. So those are just a few types of defects you can find. All right. Now there's also many challenges involved, which when it comes time to inspecting tube exchangers. So first of all is whatever instrument you're using, whatever solution you want to use, you want to make sure that that solution can inspect ferrous, non-ferrous, finned, and unfinned tubing. So all of these are just different ways that manufacturers make their tubes, and no manufacturer makes the tube the same way. And also every exchanger is used in a different market, a different plant. So you have many types of combinations possible. Sometimes the inspection equipment can be complicated to use, whether it be the software, the connection, just the overall unit itself. It can be complex. So we have to make sure that it's relatively easy to use, just to make it a lot more user-friendly. Now, inspection equipment can also be large and cumbersome. So if it's very large, very heavy, if you have a lot of room, it doesn't really matter. But if you're in a tight area, you're on top of an exchanger tower, sometimes the place is very limited. So if you can reduce the size of the equipment, it gets a bit safer for everyone around. Some of these exchangers are also in hard to reach places. As I mentioned before, sometimes they're on top of towers. So you have to climb the ladder, bring up your equipment, and make sure everything works. We don't want people to get hurt trying to bring stuff up. So hard to reach places are kind of a big pain to deal with. Another problem is a lack of personnel. Not many people actually do tube testing. It's a eddy current technology, so being a licensed eddy current level 2 or 3, there's not many of them at least in Canada, there's not many of them. So we like to try and find a way that we can get more people into tube testing quicker. Also, other challenges is that not all defects are detected equally. So here we have the different types of technologies that this new kit can do. So we have eddy current, remote field, and near field. And we have the types of defects, so internal pitting, external pitting, et cetera, et cetera. So here, for eddy current, internal pitting, we can see that it works perfectly. We'll find it all the time. External pitting, same thing. Axial cracks, yes. Circumferential cracking, it's a yes and a no. That will depend on the probe that we use. I'll show you that later. Internal corrosion, external corrosion, and supports, we can find it really well. Now, when we get to the remote field, we can see that it's a bit different. External corrosion, yeah, we can find it easily, but the rest, it's yes, we find them, or no. So depending on what you're trying to find and what your material is and all that, you have to know the limitation of your technology. So here, near field, which you're measuring basically the internal liftoff, well, we don't really see much on the external, which makes sense because we're looking on what's going on the inside. So knowing all of this is another thing. It's like, all right, what am I looking for? What do I need to make sure this inspection works? And last but not least, the exchangers are all different. So they have different diameters, different materials, different wall thicknesses. Now, diameters will affect the fill factor of the probe you need to use, while materials and wall thicknesses will depend on the frequency used. So there is no quick solution. It takes a lot of understanding what's going on, figuring out what you need to find, getting the right probe, the right frequency. So there's a lot of challenges involved with heat exchanger inspection. So our solution is using the NORTEC 600D and a brand new heat exchanger tubing kit. So why this is a nice little feature. This is a nice little instrument because we took what the NORTEC is known for and we added tube testing to it. Now, for those who've already used the NORTEC and have used the tube testing adapters previously, we used to have 2 adapters, one for differential and one for absolute inspections using eddy current. But now we were able to put just one adapter. So one adapter will do both. So it makes it a lot easier, less material to carry around. And we still have what the NORTEC is known for as for its application-driven interface. It's easy to use with minimal training. You can locate defects close to supports because we have a mix function. you can use all your probes that you have, so your MS5800 probes work with the NORTEC. We also have the auto mix function, which makes mixing out signals you don't want even simpler. We have a probe drive selection, so we can go at 2, 4, or 8 volts. It's designed to meet IP66, so great against dust and rain. It's a field-proven instrument. It's been around for years. We've had very good reviews. It's a good instrument. It's lightweight, so if you have to bring it up a heating tower or if you're going into a boiler, it doesn't take much room. It's lightweight. You can keep it in your hands. You can get a lot of battery life. If you're doing eddy current testing, it's about 10 hours. If you're using remote field, it's a bit less because the remote field adapter is amplified. You might get between 6 and 8 hours. And the other thing is the interface has been translated, so it's available in multiple languages. So you can, if English isn't your first language, no problem. We have many other languages: French, Chinese, Japanese, etc. Okay. Now, what do you get in the kit? So what's in the box? So in the box, we have the splitter box, which is used to connect the adapter and foot pedals to the instrument. We have an ECT adapter, which is used for non-ferromagnetic tubes. So this adapter does absolute and differential signals. We have 2 adapters for near field. So we have a differential and we have an absolute. So differential is mostly for pits, and absolute, longer defects. The RFT adapter, which is right here, is used to inspect ferromagnetic tubes, and will also do absolute and differential signals. Now it also comes with the foot pedals. So we have a raised and null, as well as the foot pedal cable. So that's the entire kit. And now we'll look at a quick review of eddy current technology. So eddy current is used for conductive and non-ferromagnetic tubes. It's a very fast technique, up to 2 meters per second. With eddy current, you can actually tell if the defect is located on the ID or the OD, which is very interesting. And you can also detect defects under the support using the mix channel. Now, previously I said that we have trouble finding circumferential cracking, because of certain rules of physics. Well, the main rule here is an eddy current using bobbins creates creates this type of eddy current. And what happens is when you're trying to inspect a circumferential crack, well, the eddy current isn't distorted, so you can't see it. But if you use a TEC, which is our air conditioning probes, you can find them. I'll give you an example later on when we get to the eddy current inspection demo. Other thing, we also have remote field. So remote field, we're using a magnetic field which is much further away from what we usually see with eddy current. So the distance is about 2.5 to 3 times the OD. So this is the distance between the exciter and the pickup is about 3 times the OD over here. And what we have is we have this magnetic field which goes through the material and back into the material. So this solution is great for ferromagnetic materials. It's very sensitive to volumetric defects. It will detect pits or pitting. It won't detect a single pit, but the way that a carbon steel tube will pit usually involves many, many, many pits. So you will find your pits, and it's a very slow inspection. We're talking about 0.1 to 0.5 meters per second, and that's just to make sure that your magnetic field has enough time to cross and goes back in. So very slow. Now we have 3 types of probes. We have single exciter, dual exciter, and dual pickup. Today I'll show you the single exciter, which is very good for absolute signals, and a dual exciter, which is really good for pits and finding defects around the support. Now, the reason it's good around the support is if you have your support here, well, you still have this exciter that's reading what's going on, even if this one's dead, because a support signal will completely remove your magnetic field from entering the other one, so the other side, the other pickup. So this is why we show both models in our demo. All right, then we have near field. So near field is used for anything that is carbon steel with thin fans. So this is what we have here. We'll have a better picture later on. It's a very fast inspection. It's an ideal replacement for magnetic flux leakage, and the data analysis is very easy to do. And as I mentioned before, what we're measuring here is just the liftoff between the coil and the wall. So right here, I don't know if you can see, but we're just measuring liftoff. So it's super easy to see and very efficient. All right, key points. So before I start the demonstration, I just like to explain a few things. All right, the following demonstration will show the technologies and their functions, their functionalities. The keystrokes will not be seen. So these demos will show advanced features that might be beyond the reach of a novice user. And when in doubt, direct your questions to your local sales representative or visit our website, olympus-ims.com. Also, feel free, if you have a question, to put in the question and answer section here, and we will get to them maybe later. So if you're not used to using the NORTEC, don't worry. If you need more help, we're here to help. The whole purpose of this demo is just to show you how crisp and clean the signals are. Also, other key points, the H gain and V gain, so horizontal gain and vertical gain, must always be equal. I will be using the pedals to free up my hands. So you'll be hearing maybe a ticking sound. That's my foot pressing on the pedal. And the reason we have the pedals is to keep your hands free for the inspection at hand. So as we can see here on the picture, his hands are basically dedicated to just scanning the tubes. If we have too much clutter on the screen, I will be using the erase pedal just to get rid of it. And each technology is for a different application. So as I mentioned, there is no magic probe and magic adapter for every situation. So that's why I want to show you the 3 technologies. All right, so what we're using today for our demonstration gear, we have a NFT, so a near field calibration tube, which has tapered ends and 3 pits in the middle section. So my probe will fit perfectly in the middle section, and then when I scan it, you'll see I'll get more lift off on the ends, and we'll see it on screen. The RFT calibration tube, we have 2. We have one that has pits for differential calibration, and one that has long defects for absolute calibration. The same can be said about the eddy current calibration tube, one for pits, as well as one for absolute. We also have support rings, which are made to imitate a support, and that's very good when we want to do the auto mix function. And last but not least, we have a eddy current fin carbon tube, calibration tube, and this just shows circumferential cracking defects and stuff like that. So that one I'll show you just visually what it looks like. And we also have the probes. So we have a regular bobbin probe, which is the TEA. We have a bobbin and pancake probe, the TEC. We have a single exciter remote field probe, the TRS. We have a dual exciter remote field probe, the TRX. And we have a near field probe, the TRD. So this is what we'll be using today. And the hookup all looks about the same. So first we connect the splitter to the NORTEC. So the splitter is right here. Then we attach the adapter required over here. We attach the foot pedal cable here to the foot pedals. And then we just select the right probe and the right calibration tube. So for differential, we'll be using the differential eddy current tube and with support and a regular TEA probe. So now we're going to switch over to the NORTEC. So now we see the NORTEC right here. The NORTEC's on over here. And this is what the calibration tube looks like. So we have a hole that's covered here. Then we have an 80, 60, 40, and 20% pit over there. Okay. So to simplify, I've created pre-saved files. So we're just going to load the first one, which is eddy current differential. Now we're going to load that. Now this file already has the auto mix function enabled. So what we're going to scan, so first we're going to null, we're going to bring all the points back. Now what we have here is frequency 1 is right here. Frequency 2 is in a strip chart kind of look. And we have the mix channel. So what I'm going to do first is I'm going to scan just the support. Okay, so what you should see is how the support signal appears on frequency 1 and 2, but there's nothing on the mix. So with the auto mix, we're able to completely remove that signal. Now, you might be wondering, all right, well, that's pretty cool, but why? I'm going to show you something else now, and that's a whole signal, okay? The hole has been calibrated about 40 degrees and about 6 divisions on frequency 1. The same is true about frequency 2. And the mix channel has been slightly increased in gain just so we can see it better. So now, I'm just going to put the support over the hole, like so. And I'm going to erase using my foot. And now I'm going to scan the hole, which now has a support over it. So what is interesting to see here is how frequency 1, you mostly see a support signal. Frequency 2, you kind of see it too, but on the mix, you just see the hole. So using the auto mix function, it's really easy to find defects under supports. And I'll just scan the entire tube with all the remaining defects. So there's our defect, another one, and we have an ID right here. So that's for eddy current differential. Very crisp signal, very fast scanning speeds, very simple to use. All right, now we're going to switch over to the absolute. So I'm going to load the eddy current absolute setup file. I'm going to recall. So once again, whenever you start, you just null. All your settings have been previously set up, so we're not touch anything else. I just have to null. And what we're looking at now, so I'll show you the picture of the support of the calibration tube. Pardon me. There we go. So what we have here is we have 2 OD grooves and we have an ID groove right here. So what we did is we've calibrated the largest groove. It's about an 80% to be about 80% of the screen height. The next one's about 40, so it's about 2 up, and then we have the ID, which is over here. So what we did was we just set up the signal to say, well, look, I'm looking for anything that's over 80 should be 8 vertical bars up, and that's what we're doing. So that's all we did, and we can scan very fast, and the signal is very good. Everything is crisp, and I mean, for absolute, it's not much harder than that. That's all we have to do. We just get a good calibration tube going, make sure we know what we're looking for, calibrate it quickly, and then we move on. Okay, so now the next demo. Next demo would be remote field. So I'm just going to go back to over here. Oh, and actually before I go to remote field, this is what I was mentioning about the TEC probe. So here you have a bobbin probe and you also have pancakes. So the bobbin probe, you can actually calibrate it just like you would a normal TEA probe. But you also have the pancake coils, which you can connect and actually see circumferential cracks. So these are the cracks that we can find. Now, when it comes time to for the circumferential cracking, we don't have any way to really calibrate, so we just have to set the signal in a certain direction orientation that we feel comfortable with. So that's what we did here. We could have increased the gain even more if we wanted to, but that's what it looks like. Okay, so for remote field, we have the same type of setup. So we got the foot pedal, we have everything set up, but now we're using a dual exciter RFT probe as well as the calibration standard with holes. You'll see it later too, and we're using the RFT adapter, which is amplified. So now I will show you what the tube looks like. So this is what the tube looks like. So we have a hole here, we have an 80, we have a 60 here, and then we have like a 20 in the back. So we're just going to go and scan that. And this one also has auto mix made. Oh, right. So here, the menu on the NORTEC. So this is just tell you what you're using now. So we have the probe model, which is the adapter. So it sees it's the RFT adapter. And the type of probe, serial number, well, it's actually the serial number of the adapter, not the probe itself. So every time we switch, that's what we see. And with every adapter, you're only allowed to select whichever application works for that adapter. I'm using remote field, so of course ACT and NFT have been blocked out, so I can't use those. So you can't accidentally pick the wrong scanning technique, inspection technique. So now we're going to go into differential. So we'll be taking pitting and wear. So first thing, as always, null. And then you want to calibrate your signal, your whole signal straight, so vertical. In this case, I'll just load up the RFT, make it quicker. So once again, we have the frequency 1, the auto mix, and we have the strip chart with frequency 2 on the bottom. So this is the whole. Then we can keep scanning. We see the other defects. Now here I'm going to get close to the support. So that's the support signal. All right. So I'm going to erase that. And what I'm going to do now is I'm going to put the support close behind. So it's about halfway covered. So the hole is halfway covered by the support. I'm just going to redo the same test. I'm going to erase. And we're going to scan slowly but surely. So here we can see that on frequency 1 and frequency 2, we kind of have the beginning of the defect, and then it goes into the support signal. And on the mix channel, we actually see the vertical line, which is what we have calibrated to be a hole. So using, once again, a remote field, the auto mix function, we're able to quickly scan and still find defects close to supports. As I mentioned before, if the defect is completely hidden by the support, it's going to be very difficult because there's a lot of attenuation going on with the magnetic field into the support. But if it's close, you can still see it, and these are the air defects, which I'm just scanning to show you what's going on. And that's air liftoff. So that is remote field differential. Now we're going to be doing remote field absolute. So remote field absolute, very similar. However, instead of using a TRX probe as we used here previously, we will be using the TRS probe. And here we have 3 types of defects. We have one defect which is shallow but on 360 degrees. We have a slightly deeper defect on 270 degrees. And then we have a very deep defect on 180 degrees. Now, the reason I say that is we can actually have the RFT curve in the NORTEC. So depending on what you're trying to scan, we can actually figure out if it's on 360 all the way down to 90 degrees. So is it all the way around or halfway around or a quarter around? So that's what we're going to show you right now. So we have the calibration tube. And what I'm going to do now is, in this case, I'll show you how the application works. So we're just going to go here. So application selection, scroll down to erosion corrosion, load it up. And this is actually the full calibration. This is all you have to do. So null the defect-free zone. We're going to scan our tube. So there we go, and that's 360. We're going to press freeze because we have all the functionalities that the NORTEC can use. And we're just going to increase the gain till we have basically like that. Maybe move it over here. Bring it down a bit. So now we have our calibration is complete. I've calibrated all 3 defects on the right line, where they should be. So now I'm just pushing the probe back in. And at the end, I'm going to erase. And if we rescan, so this one will be on 180 degrees, so it goes up to 180. The amplitude is always dependent on the material loss. So there you go, 180. The next one is 270, right on the line. The last one is 360, and very shallow. So there you go. So in about 30 seconds, I was able to calibrate the RFT absolute signal to fit my calibration standard. And now if I were inspecting a heat exchanger, I would just go in, start scanning, and figure out what's going on. So that's for remote field. Last but not least, we have near field. In a sec, I'm going to go back to the presentation, stop scanning. Okay, so we go to near field. So near field, in this case, we have 2 different adapters. So same probe, different adapters. We're going to start with differential. And what I want you to see, or at least keep an eye on, is how the pits look. As I mentioned before, we have 2 taper defects at the ends, and in the middle we have 3 pits. So just look at how the pits look. And then when we switch over, we'll see how the pits look with the absolute. So give me a second. Just gonna share this so you can see better. There we go. And this is what the calibration tube looks like. So we have carbon steel tube in the middle, and these are just aluminum fins all the way around. So we'll continue. We'll load pitting. We'll go here. We'll load NFT differential. Okay. So now I'm going to null where we have full wall thickness. So in the middle, right there. I'm going to push the probe all the way out. Erase. I'm just going to start scanning. So there's 1 pit, there's 2 pits, there's 3 pits, and there's the extra taper. So here, just going to show you with the mouse, you can really see that the pits come out really strong. I mean, these are pits, they're all in the same orientation because we're looking at liftoff, so they're all in the same vertical kind of position. However, the tapers aren't too clear. Okay, the reason they're not as clear is because when you're using a differential probe, you're comparing 2 coils side by side. So as you're going through a taper, at the beginning you might have a very big difference, or at the end you might have a big difference, but all the way through they're very small difference. The difference is much smaller. So this is what we see. So using NFT differential, we really get a very clear pitting signal. So now, just going to switch over here. I'm just going to show you something quickly. So we're going to swap it out. So we're going to swap the NFT differential adapter for the absolute. We're going to use the same probe, same type of connection, but we're looking at a single coil looking throughout the entire tube. So we'll see what happens. We're going to null the same way. We're going to put it in the middle of the tube between 2 pits, and we'll null there at the full wall length, wall loss. Once again, press continue. We'll load this one. All right. So I'm nulling in the middle. We'll erase, and then we'll start. So here we go. So that's the first taper. Then we have a pit, a pit, a pit, and the other taper. So by using absolute, you can actually see that the pits are not as clear as using the differential, but the absolute signal and the taper defects are really easy to see, like very simple. So knowing this, just knowing on what kind of defect you're trying to find will help you decide which kind of adapter. But in any case, the signal is very crisp, it's clean, not very noisy. If you look here, there's almost no noise, which means a good SNR, signal noise ratio, and it's easy to use. I did the entire calibration in about 20 seconds. I was able to create these calibrations before entering this webinar and just load them up, and they still work as well as when I did them. So it's a very easy instrument to use for tube testing. So that's what I want to show you with the NORTEC. Now we'll get back here, and we'll see there's a few things I just want to mention that I don't want you to forget. So the MS5800 probes are compatible with the adapters, excluding the magnetic flux leakage probes and the iris probes. Those are the only 2 which you cannot use, but anything that's remote field, anything that's near field, anything that's eddy current will work. Okay. So if you already have probes, you can still use them. If you don't, the entire Olympus catalog is still very much available to you. We have 2 kits. So we have the full kit, which is what I showed you today. We also have an eddy current only kit. If you don't need remote field and near field technology, you can just get the eddy current kit. It's less expensive. And if you do decide you want the other adapters, well, you can just add them later on. All the adapters, everything that you were shown today can be bought separately. It only works with a NORTEC 600D Flaw Detector. Now, that doesn't mean if you have a NORTEC and it's not a D, it won't work. We just have to upgrade it because you don't have to buy a new instrument. You just have to upgrade. So there is a way to use what you already have to make sure it works. And last but not least, this will not replace the MS5800 system. The MS5800 is a more advanced tube testing instrument, more features, a bit more complicated. But this NORTEC is meant to be a cost-effective way to start tube testing. Okay. So, in conclusion, this is a quick and simple scanning instrument. The calibration process is very easy. Just showed you one here, but if you're using one with AutoMix, it takes about 2 minutes maximum. And that's like the first time you do it, and every time you do it, it just gets faster and faster and faster. It's tube testing on a budget, so if you feel you want to start tube testing, you're not quite sure, you want to try it, it's a good way to get into the business. And it also has the right technology for the right job. So you're not just limited to eddy current. You have eddy current, you have remote field, you have near field. You can inspect any combination of fin, unfinned, ferromagnetic, non-ferromagnetic material with different diameters, different wall thicknesses. So it's really a versatile instrument. Now on that, I'd like to thank you for your attention. I'd like to thank you for signing up. And if you have any questions, please feel free to write them down in the Q&A section, and I'll be more than happy to take a look at them today. If I can't answer them or if you have more questions, please visit the website, olympus-ims.com, or write to me via tubetesting@olympus-ossa.com. And I'll be more than happy to get back to you in a prompt fashion. So are there any questions? Okay, well look, if there are no questions, I thank you once again for your attention, and I'll be looking forward to your emails.
On behalf of Olympus, I'd like to thank all the attendees for joining us today and Terrence for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email with links to the archived presentation for further viewing. That's going to do it for today. Thank you again for your interest and for taking the time to attend this event. We'll see you again next time.